Hi everyone, and welcome to pre-calculus lecture number 14, and this is the real pre-calculus algebra lecture 14. And we're going to talk about graphing quadratic functions. To start off with, I'll define what a quadratic function is. A quadratic function can be put in this form: f of x equals ax squared plus bx plus c. A is the coefficient of the x squared term, b is the coefficient of x, and c is the constant term. And a, b, and c can be any real numbers except for this one thing. A cannot equal 0. So we do have to have an x squared term. B can be 0, and if it is, we won't have an x term. C can be 0, and if it is, we won't have a constant term. But if we have a quadratic function, we do have to have an x squared term. So its coefficient a can't be 0. A quadratic function is something that can be written in this form, and I'll tell you what. I'm going to call this the standard form. Now we know from what we did in previous sections that we can take f of x equals x squared and transform it into a different function through a sequence of steps. For example, we can stretch this thing vertically and what this does is it takes the graph of f of x equals x squared and it stretches it by a factor of a vertically. So all of the y coordinates will be multiplied by the stretching factor a. Y is 1 here. So the y coordinate on the corresponding part of the new graph will be a times 1. Y is 0 here. So the corresponding point on this graph will be a times 0, which is still 0. And y equals 1 here. The corresponding on the corresponding part here, the y value will be a times 1. So we've just stretched this thing out vertically. There are other things that we can do with this. For example, we can shift this thing up or down horizontally. And I'm going to call this K. I'm taking this graph, f of x equals ax squared. So ax squared is the y coordinate of every point on this graph. And I'm adding a to it. So what I'm really doing is I'm taking the y coordinate of every point on this graph and adding k to that y coordinate. That's going to shift the graph up k units. So we're going to get something like this. But we've taken this y coordinate and shifted it up k units, so it's now a plus k. Oops. And I'm taking the y coordinate of this point and shifting it up k units. So this is now 0k. And I'm taking the y coordinate of this point and shifting it up k units. So I've done a vertical stretching. I've done a vertical shift. And now I can do maybe a horizontal shift, okay? F of x equals ax minus h squared plus k. And remember what this does. If I have a plus here, x plus h, it's a horizontal shift to the left. If I have a minus h here, horizontal shift to the right. So what I'm doing is I'm shifting this entire graph h units to the right. So this point will be -1 plus h. And here's the origin. We're moving the x coordinate h units to the right. So this will be 0, 0 plus h. And we're taking this x coordinate, moving it h units to the right. So this will be 1 plus h. And you know what? I hate it when I get my coordinates mixed up. I'm taking the x coordinate here, which is 0, and moving it h units to the right. So this is 0 plus h, 0. That's the origin. Origin shifted over h units. The y coordinates here stay the same because going from here to here, I'm shifting the graph horizontally only. So the y coordinates stay the same. And what do we have? 0 plus h is just h. Okay. You know what? We know this is 0 plus h, so let me just say that's h0. The y coordinate here is a plus k. The h coordinate is 1 plus h. The x coordinate here is -1 plus h. And the y coordinate is a plus k. Now let's just analyze what we have if we have something in this form. Horizontal shift to the right, vertical shift up. So this point in particular, 0, 0, is going to be shifted to the right h units, and it's going to be shifted up k units. And this is what we're going to get for a graph. Let me clear out some clutter here. And let's just use this as our preferred form. F of x written in this form looks like this. And we're going to examine a little bit more closely what each of these three things tells us. Let's take what we've covered so far and just run with it. We have a few more things to say, but here in the bottom left, we have the graph of f of x equals a times quantity x minus h squared plus k, and this is what it looks like. Over here we have a graph of f of x equals a times x minus h squared plus k. This is what it looks like. Apparently, the values of a and h and k in this graph are different than the values of a and h and k in this graph, which is why this graph looks like an upside down version of this graph. But notice one thing. Both of these graphs are U-shaped curves that we call a parabola. Here the U is turned upright. Here the U is turned upside down. They're both parabolas. Now, it says here a parabola is symmetric with respect to a vertical line called the axis of symmetry. And that vertical line is given by the equation x equals h. Well, let me see if we can figure out what the axes of symmetry are here and here. And remember, the portion of the graph that lies to one side of an axis of symmetry has to be the mirror image of the portion of the graph that lies to the other side of the axis of symmetry. So here's what I'm going to do. To me, the portion of the graph that lies to the right of this red line is the mirror image of the portion of the graph that lies to the left of this red line. So this thing is our axis of symmetry. And the equation of that axis of symmetry is going to be x equals h. Remember, on a vertical line, the x-coordinate of all of the points are the same. So here, the x-coordinate of every point on this vertical line is h. Here's our axis of symmetry. And over here, it looks like I can do the same thing. The portion of the graph that lies to the right of this red line is the mirror image of the portion of the graph that lies to the left. So this red line is our axis of symmetry. X equals h. Now, son of a gun, this graph looks like an upside down version of this graph. And it all has to do with this constant a out front. I'm going to make that my next bullet point. Now notice this. If a is positive, the parabola opens upward, and we say that it is concave up. Well, this parabola opens upward. It goes just like that. So apparently, this graph is concave up, and a is positive. The coefficient a is positive, and that makes this thing open up. Well, what causes this graph to open up in the opposite direction? That graph seems to open up downward, and it's because a is negative. It's less than 0. Here, a is negative. The graph opens downward. We say that it's concave down. Now, is there anything that we haven't addressed with these two graphs that we should? I think so. This bullet point right here says every parabola has either a high point or a low point, but not both. And I don't know if I actually mentioned what the high point and low point were. I guess I'll do it right now. The coordinates of the high point, oh, I know. I'll do it this way. The high point or low point is called the vertex. Here's the high point. Here's the high point of the graph of this function. So this is the vertex. Every parabola has exactly one vertex because every parabola has either a high point or a low point, but not both. And whether the graph has a high point or whether the graph has a low point, we call it the same thing. We call it a vertex. So the high point or the low point of a parabola is the vertex. And what are the coordinates of this thing? Well, remember where this graph started out? It started out with the bottom of the graph at the origin. And then what happened? We shifted it up k units. So I guess the y coordinate of this vertex is k. Originally, this vertex was sitting on the origin. But remember, we shifted it up k units. So this is the y coordinate of the vertex now. And remember, this point originally was at the origin, but we also shifted it right by h units. H is the horizontal shift right. So the coordinates of this vertex are h and k. Yep, h horizontal shift right. And this guy, that's our vertical shift upwards. Now, I think we have just about everything that we need for right now to do some graphing. Take a picture of this with your mind, or make sure you have this in your notes. We're going to do some exercises now. This looks like a pretty good one to do. This is our A, and A is greater than 0, so it's concave up, or in other words, it opens upward. Here's our H, and here's our K. The axis of symmetry. Do we remember what the equation for the axis of symmetry was? Think for a moment. X equal H, that's right. So X equal 4 is our axis of symmetry. And what about our vertex? Our vertex is the point HK, and that equals 4, 2. I'll tell you what. Let's draw just that much, and then we'll see if we can figure out a few other things that will help us to add definition to the graph of this function. The point x equal 4, y equal 2 is the vertex. And the axis of symmetry is the line x equal h, which means it's a vertical line that goes right through the point x equal h. Yeah, it sure would be nice if I could draw a vertical line, huh? Well, my intentions were good anyway. Yeah, that kind of looks vertical. The same way that the Leaning Tower of Pisa is vertical. So here's my axis of symmetry. And let's see. Y-intercept. Y-intercept. I can add that. I know that the graph is going to open upward, but maybe the y-intercept will help me out here. The y-intercept is where the graph of our function intersects the y-axis. So the y-intercept is a point on this y-axis. What do we know about the y-axis? What do we know about the x-coordinate of every point on the y-axis? Isn't it true that every point on the y-axis has an x-coordinate that's equal to 0? So to find the y-intercept, we set x equal to 0, and we see what that forces y to be. So we have y equals f of x, or f evaluated at 0. We set x equal to 0, so we have 3 times, we have 3 times 0 minus 4 squared plus 2. Negative 4 squared is 16, times 3 is 48, plus 2 is 50. Yikes. In order to plot this y-intercept, I'm going to have to put a hole in the roof and climb out. I'll tell you what, I'm just going to pick this point right up here, and I'm going to say that's y equal 50. That's going to be the best that I can do. So here's a point on y-intercept, y equals 50. Okay. And the graph's going to go like this. Yeah. Oh, that doesn't look too bad. Sure wish I knew how to draw the other half of the graph. Oh, but wait a minute. We have an axis of symmetry, don't we? Every parabola is symmetric with respect to its axis of symmetry. So the right part of this graph should be the mirror image of the left part. Ah. And you know what? I know a point on the left part of this graph. Now, about how far would you say this point is from the axis of symmetry? Well, the x-coordinate here is what? We're on the y-axis, so the x-coordinate here is what? 0. And like a real moron, I didn't help myself here. This is the line x equals h. But here h is 4, isn't it? So x equals 4 is the axis of symmetry. Forgive me, I'm on autopilot again. The x-coordinate here is 0, and this is on the axis of symmetry, so the x-coordinate here is 4. How far apart are these 2 points? X equals 0, x equals 4. 4 units, right? And by symmetry, that means that there's a point 4 units on this side of the graph. I'm going to draw that point right now. X equals 8, y equals 50. Yeah, that looks about right. And yeah, that wasn't half bad. It was all bad. Okay, that looks a little better. And this is our graph. F of x equals 3, x minus 4 squared plus 2. And notice a is 3, and that means a is positive, so the graph opens up like this. Oh, let's see, maybe we could graph x-intercepts. And you know what? We don't have any. And here's the reason. The vertex 4, 2 lies above the x-axis. The vertex lies above the x-axis, and the graph opens up from there. The vertex is above the x-axis, and the graph goes uphill from there. So there's no way that this graph can cross the x-axis. So if we try to find the x-intercepts, we're not going to succeed. Let's do another one. Okay, here's a new example. F of x equals negative 2, x plus 3 squared minus plus 2. And you know what? Since our preferred form was sort of f of x equals a times quantity x minus h squared, let me rewrite that just slightly. Okay. So we have A. A is negative So we expect that this opens downward, or another way of saying that, it's concave down. This thing is our horizontal shift to the right. You know what? What the heck? I'm just going to leave it the way it was, because we've been working with this already. We've worked with this a lot. Nope, you know what? I changed my mind again. X minus -3. And we're going to call this our H. And we're going to call that our K. So H is -3. And that means that our axis of symmetry is x equal -3. Yep, I think I did a good thing writing it in this form, because when we're looking for axis of symmetry, we want in parentheses x minus something. The point HK is our vertex, and that's going to be -3, 2. Holy moly. And what about a Y-intercept? Every quadratic function has a Y-intercept. They may or may not have x-intercepts, but every quadratic function has a y-intercept. And to get that y-intercept, we set x equal to 0 and solve for y. So we set x equal to 0. Y and f of 0 are the same thing. -2 x minus -3 squared plus 2, and x is 0, forgive me. So 2 times x, or 2 times 0, minus a -3 squared plus 2. -3 squared is 9, times -2 is 18, plus 2 is 16. Okay, let's see. -2 times 9 is -18, plus 2, -16. There, that looks a lot better. And let's go with that right now. The vertex is -3, 2, and the thing opens downward. There's our vertex. And our axis of symmetry is x equal -3. So let's draw that axis of symmetry here. So we have a vertex, we have an axis of symmetry, but we have a y-intercept -16. Holy moly. Holy moly. Okay, -16 on the y-axis, or maybe I should write x equals 0, y equals 16. And we have symmetry working for us, don't we? How far is this point on the graph from the axis of symmetry? X is 0 at this point, x is -3 here. So by symmetry, we ought to find the mirror image of this point 3 units to the other side. And let me measure this very precisely. Okay. Does that look not too bad? Let's see, this thing has a vertex above the x-axis. And A is negative, so this thing opens downward. It's going to cross the x-axis. Maybe we should try to find our x-intercepts. And to do that, we set y equal to 0. So 0 equals y, which is f of x, which equals -2, x plus 3 squared plus 2. Which equals -2 x squared plus 6x plus 9 plus 2 which equals -2x squared minus 12x plus 8, no, minus 18, minus 2. So that is negative 2x squared minus 12x minus 16 0 equals negative 2x squared minus 12x minus 16. And if we multiply or divide both sides by negative 2, 0 equals x squared plus 6, x plus 8. Holy moly. 0 equals, I can't believe this is going to work. X plus 4, x plus 2, 4x, 2x is, holy moly, that works. X equals negative 4 and negative 2. Oh, wow. So this is a point, negative 4, 0. And this is a point, 2, 0, negative 2, 0. We were really lucky there. And I think maybe I better move these points down just so that everything will be drawn closer to scale. No, that's not half bad. It's all bad. Oh, excuse me. And you know what? I forgot to label this point. But over here we have 0, negative 16 is 1, 2, 3 units from the axis of symmetry. So if we go 3 units this way, we're going to be at negative 6, negative 16. So the distance here is 3 units and 3 units. Okay. And this is the graph of the function. F of x equals negative 2, x plus 3 squared plus 2. Our book, believe it or not, talks about increasing or decreasing. I wish they wouldn't do that. But you may have some homework exercises that talk about that. So I'm going to address increasing and decreasing using this function as an example. Increasing and decreasing. Some of our homework exercises are going to ask for it. So here's the bottom line. A function f of x is increasing on an interval exactly when the graph goes uphill as we move from left to right along the graph. So let me start at this point. And as I'm moving along the graph, I am going from left to right. I am going from left to right. And as I do, the graph goes uphill. So from negative x equal negative infinity to x equal -3, this graph is going uphill. So this graph is increasing on the interval negative infinity to -3 on the x-axis. Increasing, and let me say over the interval. Negative infinity to -3 on the x-axis. Now let's start at this point and we'll continue to go left to right. Notice when the function is increasing, we go left to right. Notice when the function is decreasing, we still go left to right. So let's continue moving left to right, starting at x equal -3. And as we move from left to right along the graph goes downhill. So the graph is decreasing over the interval -3 to infinity on the x-axis. Now let's look at an example where it's a little bit more obvious. This is going to be a little bit more obvious. I'm going to move along the graph starting at 0 on the x-axis. I'm going to move along the graph and I'm going to go from left to right. As I do, the graph goes uphill until I reach x equal 1. So on the interval from 0 to 1, I'll say increasing. And they want us to use open intervals, I think. So on the interval from 0 to 1, the graph goes uphill. F of x is increasing. Now, I start here at x equal 1, and what happens? The graph goes downhill until I reach x equal 3. So on the interval from 1 to 3, as I move from left to right, the graph goes downhill, so the function is decreasing. And then starting at x equal 3 and going to x equal 4, the graph goes uphill again. So the function is increasing on the interval from 3 to 4. You know, sometimes bad things happen to good people, and this is one of them. That we may have a quadratic function given in standard form, and we may have to graph that function. Since it's in standard form, we don't know what the vertex is. We don't know what the axis of symmetry is. The only thing that we do know is whether the graph opens upward or downward. This A in the standard form is exactly the same A in the preferred form that we've been using. So maybe I should write that down. The constant A is the same in both forms. So if A is greater than or equal to 0 here, the graph is concave up, it opens upward. If A is less than 0, the graph opens downward like this, it's concave down. So if we have the quadratic function defined in standard form, we do know a little something. We know whether the graph of the function opens up or whether it opens down. Other than that, we don't know much. So here are a few things we need to know in case we're graphing a quadratic function and it's given to us in standard form. Here we go, some relevant information. If we have the graph in standard form, the axis of symmetry is given by x equals negative b over 2a, where b is the coefficient of x and a is the coefficient of x squared. So this actually is the x-coordinate of our axis of symmetry. It's also going to be the x-coordinate of our vertex. And to get the y-coordinate, we just take the x-coordinate and plug it into the function. So actually, if we have to graph a quadratic function and it's given to us in standard form, it's not the end of the world. We can deal with this pretty effectively. Let's look at an example. Graph f of x equals 2x squared minus 8x plus 10. This thing right here is our A. A equals 2. So the graph opens upward. In other words, concave up. This thing, this is our B. So B equals negative 8. And the axis of symmetry x equals, do you remember what it was? X equals negative b over 2a. So that's going to be negative 8 on top and 2a on the bottom. Is that right? Negative and negative 8 is 8 divided by 4 is 2. Yep, okay. So axis of symmetry, x equals 2. And vertex, negative b over 2a, and f evaluated at negative b over 2a. So x is 2. And what do we get when we evaluate f at 2? 2 squared is 4 times 2 is 8, minus 8 times 2 plus 10. So we have 8 minus 16 is negative 8 plus 10 is 2. Oh, that's convenient. The vertex is x equal 2, y equal 2. Okay. Now let's do y-intercepts, or rather just y-intercept. There's only one. And what do we do to get the y-intercept? The y-intercept is where the graph crosses the y-axis. So the y-intercept is a point on the y-axis, which means that the x-coordinate is 0. So here's what we do. Set x equals 0 and solve for y. Okay. Y equals f of 0, which equals 2 0 squared minus 8 times 0 plus 10. Okay, y-intercept is 10. X equals 0, y equal 10. That's our y-intercept. And let me plot these things now. That's our y-intercept. My goodness. I'm not gauging these things very well, am I? That's our vertex. And let me move it a little bit over here. And the axis of symmetry runs vertically through that vertex, doesn't it? We can use symmetry, right? Let me write that down. We have our y-intercept, x equals 0, y equals 10. How far is this point from the axis of symmetry? And remember, the axis of symmetry is x equals 2. So right here, x is equal to 2. Right at the y-intercept here, x is equal to 0. So how far away are they? 2, 0, 2 units away. So by symmetry, we should have the mirror image of this point appear on the other side of the axis of symmetry. So we go from x equal 2 units to the right, that's x equal 4 and y equal 10. And hey, now we got a graph that looks like something. And we sure do. That's a nice graph. Now, let me preach something else. We didn't compute the x-intercepts here. And for once today, I'm not flying on autopilot. I realized something without having to shame myself by saying, you know, I should have thought of that earlier. But here's what I'm getting at. Speaking of x-intercepts, I ain't got none. Now, how do I know that? I can approach this two different ways. The first thing is I've identified my vertex. The vertex is either the high point or the low point on the graph. My vertex is at x equal 2, y equal 2. My vertex lies above the x-axis. And remember our old friend A here? A is positive. A is positive, so we said this graph is going to open up. We're at the vertex, which is above the x-axis, and the graph opens up. The graph's going to go upward from this point. So there's no way in the world that this graph can intersect the x-axis. The vertex lies above the x-axis and the graph goes upward from the vertex. So as far as x-intercepts go, ain't got none. Now, suppose that I had been flying on autopilot, as I'm ashamed to admit I do sometimes. And I'm doing math, but I'm not really thinking about what I'm doing like I should be. When we're doing math, we need to think, and sometimes I do, sometimes I don't. And if I've been flying on autopilot, I may not have reasoned this way. And I would have tried to find my x-intercepts. Now, the x-intercepts are the points on the x-axis where the graph crosses the x-axis. And where the graph crosses the x-axis, that's a point on the x-axis. Well, the x-axis is the set of all points whose y coordinates are 0. So right where the graph intersects the x-axis, y has to be 0. So for x-intercepts, set y equals 0 and solve for x. And so we have 0 equals y, which equals f of x, which equals 2x squared minus 8x plus 10. So we have 0 equals 2x squared plus 8x plus 10. And I'm going to write it this way. 2x squared minus 8x plus 10 equals 0. And I can work with numbers like this, but I'd rather not work with large numbers, and I can see all of these are even numbers. I can divide both sides by 2 and make things a little bit simpler, so I'll do that. And I look at this thing and I'm thinking, I'm not sure exactly how this factors. Does it factor? Maybe it does, and maybe I'm just so tired I can't think. So what do I do in a case like that? I use the quadratic formula. The quadratic formula will give us the solutions to this equation, if there are any. And a is 1, the coefficient of x squared is 1. The coefficient of x is b, -4, and the constant term is c, 5. So I use my quadratic formula. I have x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And I just plug this in for A and plug that in for B and plug that in for C and turn the crank and out pops the answer. -b, so I'll have -4 plus or minus b squared, so that's -4 squared minus 4 times A times C. A is 1, C is 5. Over 2 times A. And so x equals 4 plus or minus the square root of 16. 4 times 1 times 5 is 20. All over 2. 4 plus or minus 16 minus 20 is -4. All over 2. And now you know what? Now I know something's wrong. I have a negative number under the radical, and that's not going to give me a real number. And in these graphs, I'm looking for x values that are real numbers. So as soon as I see a negative under the radical, it tells me a few things. It tells me that the quadratic expression doesn't factor. It also tells me no real solutions. Well, no wonder I couldn't factor this thing and solve for x. This thing doesn't factor, and there are no real solutions. So as soon as I get here, I realize I have no real solutions. And what was it that I was looking for by getting solutions to this equation? I was looking for the x-intercepts. The solutions to this equation are the x-intercepts, and there aren't any, no real solutions. So that tells me no x-intercepts. Now I should have been able to reason it out by saying my vertex is above the x-axis and A is positive, so the graph opens up. But if I'd been cruising along on autopilot, I might not have thought of that. And so this is how I would have gone about trying to find the x-intercepts. And as soon as I came to this point where there was a negative under the radical, I'd go, there aren't any x-intercepts. Okay. So this graph is done as well as anybody could do it. It's a beautiful graph. Let me just check my notes and see if there's anything else that I should tell you. Yeah, there are, but I think they're going to have to wait for another lecture. John 16:12, Jesus said to his apostles, I have many things yet to say to you, but you are not able to bear them at present. We've reached the point right here where we're bordering on information overload, so now is a good place to stop. And we will continue lecture 14 tomorrow.